Pulsar wind nebulae shine across the spectrum, flooding the Milky Way with long-lasting gamma-ray glows that shape our view of the galaxy. How do these bright, multi-wavelength beacons influence the cosmic landscape we observe? Welcome to Cosmic Enigma. Stay with this investigation as we follow pulsar wind nebulae deeper into the cosmic engine room. The interaction between the relativistic pulsar wind and its confining ejecta gives rise to a wind bubble bounded by a strong magneto-hydrodynamic termination, shock. This shock literally terminates the wind. At its surface, plasma is heated due to randomization of bulk motion, magnetic field is dissipated, and particles are accelerated. This termination shock is the first critical step in transforming the pulsar's rotational energy into the high-energy particles that will later produce the nebula's multi-wavelength. Understanding this process is essential to unraveling the power of these cosmic engines. The termination shock is a fundamental concept in pulsar wind nebula physics, and it sets the stage for the entire energy conversion process. Without this shock, the pulsar wind would simply stream outward without producing the bright emission we observe. This termination shock is where the pulsar wind is terminated and particles are accelerated. Several alternative acceleration mechanisms have been proposed, but their viability depends on the windine's magnetization and composition. Unveiling the windine's magnetization and composition is essential for understanding particle acceleration. Magnetization refers to the ratio of magnetic to particle energy, while composition indicates whether the wind is dominated by electron-positron pairs or includes ions. To understand particle acceleration, it becomes essential to unveil these two properties. This can only be assessed through detailed dynamical and radiation modeling of these systems. By simulating the flow and emission, astronomers can infer the winddive's true nature. This remains a central challenge in high-energy astrophysics. The exact acceleration mechanism is not settled, driving the need for more sophisticated models. Understanding these properties is key to determining which acceleration mechanism dominates. Only by combining multi-wavelength observations with advanced simulations can we hope to unlock the secrets of particle acceleration in these extreme environments. The flow magnetization and composition remain elusive, but progress is being made through detailed modeling. Around a spinning pulsar, the light cylinder marks the boundary where co-rotating magnetic field lines can no longer keep up. Inside this cylinder, the region is expected to be filled with plasma. There, particles are electromagnetically accelerated and then escape along open magnetic field lines, forming the ultra-relativistic pulsar wind. This wind is the engine that powers the nebula. The light cylinder is the birthplace of the wind, where rotational energy is converted into particle kinetic energy. The light cylinder is a fundamental concept in pulsar physics. The exact location of the light cylinder depends on the pulsar's spin period, but its role is universal. By studying the windine's properties, we can infer the conditions inside the light cylinder. The light cylinder is a key region in the pulsar wind system, and it is critical for the formation of the ultra-relativistic wind. The light cylinder is the birthplace of the ultra-relativistic pulsar wind. Among the many pulsar wind nebulae, one candidate is the Crab Nebula, which is a pulsar wind nebula. Diffusive shock acceleration in supernova remnants was considered the primary acceleration process of galactic cosmic rays. However, the Crab Nebula challenges this view by showing that pulsar wind nebulae can also accelerate particles to high energies. The Crab Nebula is a key laboratory for studying these processes. The Crab Nebula is a cornerstone of high-energy astrophysics. Understanding the Crab Nebula is essential for understanding the high-energy universe. Share your thoughts on the Crab Nebula in the comments. The Crab Nebula provides a unique opportunity to test models of particle acceleration. The Crab Nebula is a prime example of a pulsar wind nebula, and it is a key object for studying particle acceleration. The Crab Nebula is a pulsar wind nebula, and diffusive shock acceleration in supernova remnants was considered the primary process for galactic cosmic rays. Realistic population-level predictions have so far lacked any detailed treatment of the reverberation phase, when the nebula is compressed by the supernova remnant reverse shock, significantly altering its dynamics and radiative spectrum. To address this, researchers employed a hybrid framework that combines a thin shell dynamical model with a Lagrangian treatment of the SNR structure during reverberation, allowing for self-consistent evolution of thousands of pulsar wind nebulae across all stages up to 10 circumflex 5 years. This framework marks a significant step forward in population studies. It allows for a more accurate understanding of the nebula's evolution. The reverberation phase is crucial for understanding the full life cycle of these nebulae. This phase is not just a detail, it fundamentally shapes the nebula's evolution and its gamma-ray emission. The hybrid framework is a significant advancement in modeling. It provides a self-consistent treatment of the reverberation phase, which was previously ignored. The hybrid framework allows self-consistent evolution of thousands of PWNA across all stages up to 10 circumflex, 5 years. Extended structures have been observed around a couple of systems, such as the Lighthouse, Nebula, and with the recently increased number of detections, they now seem a rather common feature of evolved nebulae. The generally accepted interpretation is that they are produced by high-energy particles close to the maximum limit of the potential drop, leaking from the Bauschock Nebula, and then producing emission via synchrotron radiation in the local magnetic field. These structures provide clues about the maximum energies achievable in pulsar winds. Understanding these extended features is an active area of research with implications for cosmic ray propagation. The Lighthouse Nebula is a prime example of such a structure. These structures are important because they reveal that particles can escape the nebula and travel into the interstellar medium. They provide a direct link between the pulsar wind and the surrounding environment. The Lighthouse Nebula is a key example, showing how particles can escape the nebula and light up the surrounding medium. These structures are a testament to the enduring power of pulsar wind nebulae. They are a common feature of evolved nebulae, and their study is crucial for understanding the late stages of pulsar wind nebula evolution. Extended structures are now recognized as common features of evolved nebulae. Pulsar wind nebulae are fascinating systems and archetypal sources for high-energy astrophysics. Due to their vicinity, brightness, multi-wavelength emission, and long-lasting gamma-ray glows, modeling their properties is particularly important for the correct interpretation of the visible galaxy. They are not just isolated phenomena, they shape our view of the galaxy's high-energy landscape. Understanding them is key to understanding the universe's most extreme environments. The investigation into pulsar wind nebulae is far from over, and many questions remain. How exactly does the termination shock accelerate particles? What is the true composition of the pulsar wind? By studying pulsar wind nebulae, we gain insight into the most extreme physics in the cosmos. They are integral to the high-energy universe. These systems continue to challenge our understanding of particle acceleration and magnetic fields. Modeling their properties is important for interpreting the visible galaxy. Subscribe to keep exploring the universe's most powerful power plants.